Hope you're trying to have a productive day. In this video, we will be going through yet another past paper question. This question will be question number 3 from the Physics Unit 1 Paper 2 for CAPE. Let's get right into it. A resistance thermometer and a thermocouple thermometer are both used at the same time to measure the temperature of a water bath. Explain why the thermometers may record different temperatures even though they are calibrated accurately and are at equilibrium. So this is more like an explanation rather than a calculation, but I will draw a couple of things to kind of show you why the temperatures might be different. Now, when it comes to thermometers work by calculating a temperature that is related to some kind of thermometric property. A thermometric property, in simple terms, is a property of matter that varies with temperature. And in the case of thermometers, we want that property to vary linearly with temperature. Let me show you what I mean by varying linearly with temperature. Let's say we have a graph of some kind of property on the y-axis versus temperature on the x-axis. When a property varies linearly with temperature, the graph will look something like that. A line, right? And the gradient of this line can give you some information. When it comes to the two thermometers mentioned here, we have a resistance thermometer. Now, the resistance thermometer, the thermometric property that is used or that is measured is actually resistance. And the resistance is typically the resistance of a wire. Now, resistance varies with temperature, similar to how this graph would indicate, but for resistance, it looks more like this. It's not perfectly straight, but for the most part, it's basically a straight line. That's for resistance. Now let us look for the thermometric property of a thermocouple. For a thermocouple, the thermometric property is EMF, in this case, voltage. So the graph for how the EMF varies with temperature would look something like that. And as you can see, it's not the same as the graph for resistance. In other words, the thermometric properties that are used to measure the temperature are not the exact same, and as such, the thermometers will not give the same temperature measurement even though they're measuring the same thing, right? That can be a reason as to why the resistance thermometer and the thermocouple give different temperature readings even though they're measuring the same thing. Their thermometric properties do not show the same relationship with temperature. So briefly explain why the thermometers may record different temperatures. You can put what I just said into your own words. You can summarize it, and you'll need to get into the habit of putting things into your own words and also maybe summarizing them a little bit, but ensuring that the crucial bits of information and terminology are included in your answer. Moving on to part B. What is meant by the term absolute zero of temperature? Well, the absolute zero of temperature is the lowest theoretical value that a temperature can be. This value is assigned a value of 0 Kelvin or negative 273.15 degrees Celsius. So 0 Kelvin, notice it is not degrees Kelvin, it's just 0 Kelvin, not 0 degrees Kelvin. 0 Kelvin and negative 273.15 degrees Celsius are the same temperature, but they're in different units, right? But they're the same temperature. And that's what is meant by the absolute zero of temperature, the lowest temperature that exists, at least theoretically. Part 2, state how the absolute thermodynamic scale of temperature differs from other temperature scales. The absolute thermodynamic scale of temperature uses the triple point of water as its reference point, whereas other temperature scales use the boiling point of water as the upper fixed point and the freezing point of water as the lower fixed point. The absolute thermodynamic scale uses the triple point of water as its reference. So that's why it's different. And by the way, the triple point of water is 273.16 Kelvin or 0.01 degrees Celsius. Moving on. The temperature of a water bath increases from 50.00 degrees Celsius to 80.00 degrees Celsius. Determine in Kelvin and to an appropriate number of significant figures the temperature of 50.00 degrees Celsius and the change in temperature of the water bath. Now, The actual calculations are not very difficult for this question, but the significant figures might be a little bit of a challenge if you haven't been dealing with them thus far. So when we say 50.00, it is not the same as saying 50. 50 and 50.00 have different numbers of significant figures. The significant figures in 50.00 would be 4. And it's 4 because the 2 zeros at the end of the decimal place indicate that those 2 zeros are known relatively accurately, right? Meaning you can measure down to the 100th of a Celsius degree, right? That's why we have the extra zeros there. It's to show that it is accurate to that degree that we showed it as. If it was just 50, then it would only have one significant figure, and that would be the 5. So let us do this calculation. We're going to basically convert 50.00 degrees Celsius to Kelvin. The way we do that is we simply add 273.15 to the Celsius temperature, and the result of that addition is going to give us the Kelvin temperature. So in this instance, it would be 50.00 plus 273.15, and that gives us an answer of 323.15 Kelvin. Now with this answer, do we have the right amount of significant figures? Well, when it comes to adding numbers, how do you determine how many significant figures the sum should have? Well, the amount of decimal places in this case in the sum should match the amount of decimal places in the data point that has the least number of decimal places. In other words, if you add two numbers and one has one decimal place but the other has two, the final answer should have one decimal place because the data point with the least number of decimal places had one decimal place. That's why. So you look at the number of decimal places in the data point that has the least number of decimal places, and that is a number of decimal places that should be in your final answer. In this case, both of the data points or both of the numbers have two decimal places, so the answer is going to have two decimal places, right? So this would be the answer for that question. Now the temperature difference they want us to work out, or the temperature change. So the temperature change would be the final temperature minus the initial temperature. So it would be 80.00 minus 50.00. And that would give us 30. And the same rule that applies for adding also applies for subtracting. So in this scenario, both of the data points have the same amount of decimal places. So the answer is going to have that number of decimal places, which is 2. So the final answer is 30.00 Kelvin. And that would be the change in temperature. An empirical centigrade temperature can be determined and defined in terms of any suitable thermometric property. Select one type of thermometer with a suitable thermometric property and describe briefly the procedure and necessary readings to be taken in order to use this thermometer to determine a random temperature. Theta. Basically, it wants us to state a thermometer, the thermometric property, and describe the steps that we would take to measure on that thermometer a random temperature, theta, right? So the first thing you do is select your thermometer. You can select the thermometers that you want or the type of thermometer that you want. But for this example, I am going to select the constant volume gas thermometer. So that's a thermometer. What is going to be the thermometric property? The thermometric property is really the pressure of the gases, but the pressure measured in the constant volume gas thermometer is going to be directly related to the height of mercury in the open end of the U-tube manometer. So it's going to be height. That's going to be what we use in our equation. It's going to be the height of the liquid in the open end of the U-tube manometer, right? So that is going to be the thermometric property, and that thermometric property is based off of the pressure. Now describe the procedure and the necessary readings to be taken. The procedure, I will briefly describe it. First, you're going to set up the apparatus as you normally do. Then you are going to take some measurements. You're going to measure the height at 0 degrees Celsius. Then you're going to measure the height at 100 degrees Celsius. Then you're going to measure the height at the unknown temperature, in this case, the random temperature that you're trying to find. So you're going to have 3 height measurements. And when you're measuring the height, you're going to ensure that the height in the closed end of the manometer, the one that's attached to the glass flask in this case, is kept at the same level to ensure that the volume within the glass flask is the same, which is why it's called a constant volume gas thermometer. After you've measured the height at 0 degrees Celsius, 100 degrees Celsius, and the random temperature, you are then going to use this equation to arrive at the temperature of the, random temperature that you're trying to measure. What is that equation? You could derive this equation in multiple different ways, but I'm not going to do that right now. I'm just going to write it out. So this equation is basically called the equation of the Celsius scale, and it goes like this. The temperature that you're trying to measure, or the unknown temperature, or the random temperature, here, we'll call it theta x, is equal to, in our case, the height of the liquid at that temperature, the height at x, minus the height of the liquid at 0 degrees Celsius, right? And then we're going to divide that by the height at 100 degrees Celsius minus the height at 0 degrees Celsius again. Then we're going to multiply this answer after we've subtracted and divided. We're going to multiply by 100. And that will give us our random temperature in degrees Celsius. You again can take what I just said, summarize it, put it in your own words. Moving on to part E of the question. The relationship between the resistance R of a wire at temperature T in degrees Celsius as measured by a mercury thermometer and the resistance R0 at 0 degrees Celsius is R is equal to R0 divided by 1 plus alpha times T squared, and T in this instance is the temperature. Alpha is going to be 5.0 times 10 to the minus 5 per degrees Celsius squared. So that's the information that they gave us. Now, calculate in terms of RO the resistance of the wire at 100 degrees Celsius and at 80 degrees Celsius as measured by the mercury thermometer. So you're going to have to read this question maybe a couple of times. Don't take too long though. And you're going to find out what it is asking of you. When you've read and you've understood, then you can move on into some calculations. So basically the question wants us to find the resistance, right? Right there. Right there, the resistance, right? The resistance is this, is R. But it wants us to find the resistance in terms of RO, which means that the final answer must have RO as a part of it. Now, we're going to find that resistance at 100 degrees Celsius and at 80 degrees Celsius as measured by the mercury thermometer. So how do we do that? Well, we just use the equation they gave us here, or the relationship, where we're going to plug in a value for T and then just solve the equation. So let us get into doing that right now. So R was equal to RO, which is the resistance at 0 degrees Celsius, divided by 1 plus alpha times T squared. So all we have to do is just plug in the values and then solve for R. And remember, RO is going to be a part of the answer. So we rewrite our RO and then we plug in the values. So it's going to be 1 plus alpha. Alpha was stated to be 5 times 10 to the minus 5. And that's going to be multiplied by 100 squared. Right? When we do that, we'll get RO divided by 5 times 10 to the 5 multiplied by 100 squared. That gives us 0.5. So now we get, oh, this should be RO. We get RO over 1.5. RO over 1.5 is the same as saying RO times 1 divided by 1.5. And 1 divided by 1.5 is 0.66 recurring. So we get R is equal to the final answer of 0.67 RO. So that is the resistance at 100 degrees Celsius. We're going to do the same process to find the resistance at 80 degrees Celsius. So this is the resistance at 100. Let's find the resistance at 80. That is going to be RO divided by 1 plus 5 times 10 to the minus 5 times 80 squared. And that gives us basically RO divided by 1.32. And that gives us an answer of 0.76 RO. So we have calculated in terms of RO the resistance. And as you can see here, our final answers of 0.67 RO and 0.76 RO, they both have RO. So they're in terms of RO because RO is a part of the final answer. Next part of the question, actually the last part of the question. If the resistance of the wire is used as a thermometric property, what is the temperature reading of the resistance thermometer when the reading on the mercury thermometer is 80 degrees? So it's going to ask us to use a thermometric property to find temperature. How do we do that? Well, remember back up here, we said that we could use a Celsius scale. So all we're going to do is replace height with resistance, and that will give us our answer. So that's what we're going to try and figure out. And we're just going to basically, everywhere we have height, we replace it with R as resistance. When we plug in the values, we will calculate the temperature measured by a resistance thermometer when the mercury thermometer measures 80 degrees Celsius. So are the temperatures going to be the same? Are they going to be different? Well, let's find out. So let's rewrite the Celsius scale. It's going to be theta at 80 is equal to, in this case, it's going to be R at X, right? R at our temperature. If we go over here, we had X and X is over here. So this is the temperature at X. This is the height of the mercury column at X. So over here, if this is the temperature at 80, then this must be the resistance at 80. There we go. And then we had minus HO. So instead of HO, we're going to have the resistance, RO, which is the resistance at 0. Then we're going to divide that now by the resistance at, what was down here? 100. The resistance at 100 degrees Celsius minus the resistance at 0. And we're basically going to multiply all of this by 100. So that's all we have to do. But we have a bit of a problem. The question never once gave us the actual value for any resistance. It never gave us the resistance at 80. It never gave us the resistance at 0. And it never gave us the resistance at 100. So what do we do here? Well, the question had you work out the resistance, even though it didn't give you a number, it told you to work out or calculate the resistance in terms of RO. That's what we just did. Meaning that R80 can be written in terms of RO. When we calculated R80 in terms of RO, we got 0.76 RO. So now we have 0.76 RO minus RO. And then down here, when we had the resistance at 100 in terms of RO, that was 0.67 RO. And then we have minus RO. Now we can do some things. We can factor out RO from the top part of the equation. When we do that, we end up getting 0.76 minus 1 times RO. This is what the factored form of the top equation looks like. And you can see that it's factored because if I multiply RO by 1, I get RO. So I would get minus RO. And if I multiply RO by 0.76, I get 0.76 RO. So when I expand this, I get this, which is why over here is the factored form of over here. We're going to do the same thing to the bottom of the equation. And we're going to end up with 0.67 minus 1 times RO. Now you can see that the RO in the top and the bottom of the equation, they cancel, which means we don't even need to know the resistance, right? Fun stuff. Oh, and by the way, all of this was multiplied by 100, and this is also multiplied by 100. So now we can just calculate using math. So 0.76 minus 1, that is going to give us negative 0.24. And then 0.67 minus 1 is going to give us negative 0.33. And then that's going to be multiplied by 100. So when we divide a negative by a negative, we get a positive. So this number is going to be positive. So it's going to be equivalent to, if you plug it in on your calculator, 0.727 times 100. So now we finally come down to the last part of the answer. We just have to multiply 0.727 by 100 and we end up getting 72.7. And this is going to be degrees Celsius, right? So basically, when the mercury thermometer measures a temperature of 80 degrees Celsius, the resistance thermometer, in this case, is going to measure a temperature of 72.7 degrees Celsius. So the temperatures are indeed different in this scenario. And if we go back to the first question, or I erased the graph, but if we went back to the first question, it's related to what we just worked out, right? You can see some linkages to it. And with that, we have come to the end of this question. So if you were able to do all of this working out and the explanations within a reasonable time frame, you would have acquired your 15 marks and you would be one step closer to getting that grade that you want on your final CAPE exam. So as always, thank you all for watching and I hope you've learned something.